Okay, so we're asked to graph this equation y equals 3 sine of the quantity 6 pi x. Now, in order to do this, we're going to look for some of the more important pieces of information. First, we'll start with the amplitude. And to find the amplitude, what we're going to do here is take our leading coefficient here, that 3. It's going to be an absolute value of whatever that number is to give us our amplitude, such as still 3. And admittedly, that wasn't spectacularly exciting, but that's the way we need to do it. Alright, so next one up of the pieces of information we're going to look for is the period of this function. Right, so now with the period, we're going to be looking at this as 2 pi over the coefficient of our variable inside the parentheses, so that's our 6 pi. Alright, so 2 pi over 6 pi, here the pi's are going to go away, and the 2 and the 6 will cancel to leave us with a period of 1/3. Now the next thing we're going to look for are phase shifts. And that's going to be inside the parentheses, just like the way of determining the period was. But that's going to be looking for something after this 6 pi x. We would either have a plus, some number like 7, or perhaps more like a minus 2/3, or anything along those sides, but inside the parentheses for a phase shift. Because remember, that's going to be the same as a horizontal shift, either to the left or to the right. In this case, we don't have anything added or subtracted from the x term inside the parentheses in the sine function, so that tells us then that we don't have a phase shift, or a phase shift of 0, which is nice when it comes down to graphing. Right now, we'll go ahead and look to see if we have any kind of reflections. Right, now the reflections are going to be indicated by a negative sign showing up either inside the parentheses in front of the x term, which we don't have one there, or outside the parentheses in front of the sign in the leading coefficient. But we also don't have a negative sign to go along with either of those two things. So for our reflections, we don't have any. It's kind of nice, actually. Now, the next item that we're going to look at is going to be for seeing if we have any vertical shifts. Okay, the vertical shifts are going to be added or subtracted, so that's very similar to what we were looking at when we were talking about phase shifts. But the vertical shifts are going to happen strictly outside of the parentheses of the function. In fact, it'll be separate from the function entirely. And since there's nothing added or subtracted on after this 3 sine of 6 pi x, that tells us then that we've got nothing else that we need to worry about. If we did, what it would look like would be like a plus 4, or perhaps, I don't know, a minus square root of pi. It's any kind of number. It doesn't have to be an integer necessarily, though they typically will be. So anything like that, where you've got an adding or subtracting from outside of the original function, that's going to indicate ourselves a vertical shift. So we don't have one of those either, so we'll call that a vertical shift of 0. Right, now the last bit of information that we're going to look at for purposes of graphing is the one that's not always shown in the various textbooks. And it's going to be that distance between key points. All right, now, the thing to remember about a key point is that it's either going to be the top of the graph point, it'll be in the center part of the graph, or often at 0, which is typically the middle line unless there's a vertical shift, or at the bottom valley of the graph. All right, so the way we find our distance between key points is we take our period, which is 1/3. We got that from this fella here. And we just take that guy and multiply him by 1/4. So I know fraction arithmetic is not always the favorite activity of any math student, really, but this one's pretty straightforward. Multiplication of fractions just takes us to top times top, bottom times bottom. In this case, we've got a 1 times 1, which is still 1, and 3 times 4, which is 12. So what this means is that every point that we care about for our key points is going to be 1/12 of a unit away from the previous point. So what we're going to do now is just take all of this information and put it together. I'm going to start by drawing our coordinate axes. Get our x-axis down here, going to left to the right, y-axis going to the up and down part. And now we are going to start by looking at our point from the phase shift. Now, since our phase shift is 0, that means we're not moving our typical starting point from the left or to the right. And with sine, that means we will be starting at 0, 0 for our origin. Sine graph typically passes through the origin. Right. Now, next, we're going to come to our next key point, and remember that's going to be pi over 12 units away. So now we're going to come over here, 1/12, and our typical graph of sine, here we'll just do a quick and dirty sketch of that guy. If we're looking at y equals sine of x, for one period, at least the period we normally see, goes a little something like this. All right, we'll go start at 0 and then go up to the top of our graph. So here, then we come back down to 0, then we go all the way to the bottom of the graph, and then we come back up again to 0. So now with our graph here, there was no reflection, so we're going to follow the same behavior as we would for typical sine. So that means at 1/12, our y value is going to be the max of our graph, which will be 3 in this case. All right, so we have our point here at 1/12, 3. And now we're adding another 1/12 again to our graph here. So 1/12 plus another 1/12 will give us 2/12. Now I know that 2/12 can be reduced down, but honestly you want to wait on doing anything of the sort as far as reducing goes until at the very last step of your graph when all of the other points have been plotted. And the reason for that is this makes your life so much easier. Now once we are at the top of our graph, just like we were here, then we move down to 0 on our regular graph of sine, so we're going to do the same thing there. And then another 1/12 will put us at 3/12, which again, yes, can be reduced, but we'll do that at the end. And that's going to take us to the very bottom of our graph here at -3. And then our next point will be another 1/12, so 3/12 plus another 1/12 will give us 4/12, and just like what we did for our regular graph of sine, we're ending here at the center or at a 0, which is helpful. All right, now what we've got here is just an outlay of 5 points. All right, so now what we're going to do is just connect the dots to give ourselves a completed graph. All right. Now, don't just automatically connect these 2 points in a straight line like so, and then bring it back down like so, wobbliness notwithstanding. The reason being is, while you're not going to be necessarily graded based on your hand drawing and your artistic eye, you do want to give some fidelity to the actual graph, meaning that these should be a nice curve. So, try to put that in as much as you can. If you need to take a stopping point here at some point, that's also fine. So like we did here at 2/12, we're going to come back down here to our -3, and swoop back up again to the 4/12. Now, some instructors are kind of sticklers for having the dotted lines going off to indicate the graph keeps going. Others could care less. I'm one of the could care less guys. But this is our graph of one complete period of our y equals 3 sine of 6 pi x. That's done using all of the various pieces of information we've got here. Now, since we didn't have a lot of additional features, we just have a relatively basic graph, and that's okay. That's allowed to happen. It is allowed to be easy sometimes. We're asked to graph the equation y equals -2 cosine of 4 times the quantity x plus pi over 4. And the first thing we're going to look for here is our amplitude, which is going to be the absolute value of our leading coefficient here in front of the cosine, which is -2, which has an absolute value of 2. So that's our amplitude taken care of. Next, we're going to look for the period. And that's typically in the form 2 pi over whatever our coefficient happens to be of our x term. Now, on the face of it, x appears to be by itself, but remember there's this 4 sitting out in front of that quantity, so that's actually going to be the coefficient we're going to be looking for. So this will be 2 pi over 4, which will reduce down to giving us pi over 2 for our period. Next, we're going to look for our phase shift. Now, as it happens, the 4 being factored out made the period slightly more irritating to discover, but actually it helps us out when it comes to the phase shift. The phase shift is just that number, pi over 4, but because it's a positive pi over 4, we know this is actually a phase shift of negative pi over 4 when it comes to the graph. Now we're going to look for our distance between key points. And to do this, we are going to take our period and our period, which is pi over 4. No, it isn't. We'll just pause that again. Next, we're going to look for our distance between the key points. Now remember, that's just going to be found by taking our period, which was pi over 2, and multiplying it times 1/4, which will give us pi over 8. Now we're on to drawing our graph of our function. So because of our amplitude, we know we're going to be falling between -2 and +2 here, and because of the phase shift, which we found to be negative pi over 4, that's going to be our starting value. And now we check out our leading coefficient in front of the cosine to verify if we're going to be starting at the top or the bottom of our graph. Remember, cosine by default starts at the top, but because it's a negative coefficient here, in this case -2 in front of our cosine, that means we are in fact going to be starting here at the bottom. So our first point in our graphing of one complete period is at the point negative pi over 4, -2. But now we need to find the remaining key points. We're going to do that by taking that negative pi over 4 and adding our distance between points to that, which was a pi over 8. Now, to get these two fractions to add together, we need to find the common denominator, which is going to be 8. So that means we would multiply the top and bottom of that first fraction by 2. So we have -2 pi over 8 plus pi over 8 to give us negative pi over 8. So that's going to be our next value in our graph. And so now we take that negative pi over 8, add another distance between key points here of pi over 8 to this to get our next key point at 0. And we're going to repeat this 2 more times. So we take our 0 and we add pi over 8 to that to get, what a surprise, pi over 8 for our next key point, and then we take our pi over 8, add another pi over 8 to get 2 pi over 8s. Now, I know this will reduce down to pi over 4, but I'm going to leave this as is. If you want to reduce, that's fine, and I would strongly urge you to wait until the very last step in the graph before you do that reducing. Reason for that is you want this to be a process that's as simple and as straightforward as possible. So if you keep reducing and then you have to go back and add the distance between key points again and then again find another common denominator, it can be kind of a hassle. So if you leave everything in its unsimplified form, it makes your life a little bit easier when it comes to putting all the key points down. Now, because cosine starts at the top or the bottom, we already determined it's going to be at the bottom of our graph. The next stop for our y values at our key point of negative pi over 8 is going to be at the midline here, 0. And then we're going to keep going up. So at 0, we're going to be at positive 2. But that's the top part of our graph. So now we're going to head back down to 0. So we're going to have the point pi over 8, 0 for our next key point. And then finally, we're here at 2 pi's over 8. And back at the bottom of our graph here at negative 2. So now that we've got those points plotted, we're just going to go ahead and connect the dots with a nice smooth curve, or at least a good approximation of one, like so. Now you can see I missed here a little bit at the top of the graph, so you can make that point a little bit bigger, and I also kind of missed here at the pi over 8. This is our graph of one complete period of the graph of y equals negative 2 cosine of 4 times the quantity x plus pi over 4. Or we're asked to graph the function y equals 4 sine of the quantity negative 2/5 x plus 6 pi over 25. Right, now the first thing we're actually going to take care of is the look of this function. Is right now with that negative sign in front of the 2/5 x, that's going to create all kinds of problems for us in pretty much every step along the way here. So what we're going to do is we're going to use the odd property of sine. Since sine is an odd function, we know that the sine of negative x is equal to the negative sine of x. So effectively what that's going to allow us to do here is we take the negative sign in front of whatever is inside the parentheses here and yank that guy out in front. So we have that outside of our sine function, so it's not going to get in the way any further. Now in order to do this for our problem, we are going to have to deal with not only the sine in front of the 2/5 x, but also that's going to affect the sine of our 6 pi over 25 as well. So we're going to just go ahead and factor that out from inside those parentheses. So we have y equals 4 sine of now negative, and once we yank that out of the 2/5 x, we have a positive 2/5 x left. And then from the 6 pi over 25, that now becomes a minus 6 pi over 25. And now we use that odd property of sine so that we can pull that negative sign out in front to leave us with y equals negative 4 sine of the quantity 2/5 x minus 6 pi over 25. And it's this modified, or if you prefer, new and improved version of our original problem that we're going to use to kind of base everything else off of from here on out. So now we're just going to take and run through the standard pieces of a graph of sine or cosine. So step 1 is going to be to find our amplitude, which is just the absolute value of our leading coefficient, which in this case is now negative 4. And its absolute value then is going to be a positive 4, so that's our amplitude. Next we're going to take our period, and we know that's going to be 2 pi over whatever our coefficient of x was. In this case that was our 2/5. But dividing by 2/5 is kind of irritating. So what we're going to do instead is write this as multiplication by the reciprocal of 2/5, which is 5/2. And here we're going to see our 2's go away. Those cancel out to leave us with a period of 5 pi. Right, next up, we look for our phase shift, which is going to be our 6 pi over 25, and divided by that coefficient in front of the x, which is 2/5. But again, this is annoying to take a fraction, divide it by another fraction, so we're going to take that 6 pi over 25 and multiply by 5/2 to get our new and improved phase shift representation here. Once the 5's go away, and the 2 and the 6 can cancel out, to leave us with 3 pi over 5 as our phase shift for this problem. Next, we're going to look at the distance between key points. Now, this is going to help us plot the relevant points on our graph, and we do this by taking our period, which was 5 pi, and multiplying by 1/4. So we get our distance between points as 5 pi over 4. Now we want to look and see if we have a reflection. So we want to check and see, do we have a negative in front of our new and improved function? And sure enough, yeah, he's still there in front of the 4. So yes, we do have a reflection over the x-axis. And while also it's true that technically this was represented as a reflection over the y-axis because the negative sign was inside the parentheses in front of the x term there, using our properties of sign being odd, we were able to pull that out and algebraically represent it as a reflection over the x-axis. And then finally, we want to look and see, do we have a vertical shift? Right? If that's going to happen, that's going to be adding or subtracting something outside of our parentheses over here. But since we do not, thankfully that means there is no vertical shift, or you can call it a vertical shift of 0. Alright, so now what we've got here is a summary of all of the things that we have just dealt with. This is our revised equation for us to graph the -4 sine of 2/5 x minus 6 pi over 25. And then here's all of our corresponding data or pieces of information, or however you feel like calling it, for the amplitude, period, phase shift, and what have you. So now we're just going to go ahead and get down to the whole graphing thing. So we're going to draw ourselves our x and our y coordinates. Now, what I've got here is just a summary of all of the information we just went through. So we have our new and improved equation here. Y equals -4 sine of 2/5 x minus 6 pi over 25. Then down below here, we've got just our relevant data that we're going to use for the graphing: amplitude, period, phase shift, reflections, distance between key points, and vertical shift. So that all but leaves us to graph. So that's what we'll do now. So we'll draw our axes, x and y. Due to the amplitude, we know we're going to be going between 4 and -4 on our graph. And then we're going to start our graph based on our phase shift here of 3 pi over 5. So we'll go ahead and put him down here. Now we need to find what our remaining points are going to be, or at least their x values. And we're going to find those x values by taking our phase shift, which is our positive 3 pi over 5, and adding our distance between key points to it, which was 5 pi over 4. All right, now we're going to be trying to add these fractions together, and of course that means we have to find a common denominator, which thankfully isn't all that challenging here since we just have a 5 and a 4, so that means our common denominator is going to be 20. So we're going to multiply our first fraction, top and bottom, both by 4, and the second fraction we're going to multiply top and bottom both by 5. So this gives us 12 pi over 20 plus 25 pi over 20, which is 37 pi over 20. Right. So that's our next point along the way here. Right. Now, rather than go back to our distance between key points as 5 pi over 4, and then take our new point and continually find a common denominator, with the work we've already done here, we know that 25 pi over 4, excuse me, 25 pi over 20 is going to be the amount we're going to add each time if we keep our common denominator as 20. So now I'm just going to worry about taking the 37 pi over 20 and add another 25 pi over 20, which will give me 62 pi over 20. And then keep going here. 62 pi over 20 plus another 25 pi over 20 will give us 87 pi over 20. And then we have one more point to go, and that's going to be another 25 pi over 20, so 87 plus 25 will give us 112 pi over 20. And yes, you can reduce the 112 pi over 20 down to 28 pi over 5 if you really want to. Honestly, it doesn't make a lick of difference as far as the graph goes, so if your instructor is going to insist on it writing everything in lowest terms, then do that reducing of 112 pi over 20 down to 28 pi over 5, and also the 62 pi over 20 would reduce down to 31 pi over 10. But honestly, I just feel that's going to get in the way here. So we'll start with our default position at sine, which is at the center line, in this case 0. Now, because we have that reflection, our next point is going to be down here at our minimum value of -4. So we have 37 pi over 20, -4 there. Then we're going to head back up to 0 for our x value at 62 pi over 20. Then at 87 pi over 20, we're all the way up at the max value here at +4. And then for the 112 pi over 20, we come back down to 0. And it's just now a matter of connecting the dots in a way that makes this look like a sinusoidal curve. So let's try to get these into as close a resemblance of a nice smooth curve as we can. If it looks like I missed that 62 pi over 20 a little bit, you can always make your point just a wee bit bigger to indicate that's where it goes. But otherwise, this is a pretty decent graph of our one complete period of y equals -4 sine of 2/5 x minus the 6 pi over 25, which is what we were looking for here. Now here we're asked to graph the equation y equals 8 cosine of the quantity -4 pi x minus 5 pi over 7, and that quantity then plus 6. So we got a little bit of everything happening in this particular trigonometric function for us to try to graph. First thing I want to deal with, though, is this negative sign that's in front of our 4 pi x. That negative is going to cause us nothing but problems if we don't deal with it right away. And to do so, we're going to remember that cosine is an even function. Alright, now what that means here is that the cosine of negative x is equal to cosine just of x, which basically tells us that we are allowed to get rid of this negative sign from in front of the variable that we're dealing with here, and that's due to the property of cosine being even in terms of functions. This is what an even function does. Now, in order for us to make that happen here in this function, we've got to take and factor out that negative from inside the parentheses. So when we yank it out from that 4 pi x, we're just left with the positive 4 pi x. But because I did it to the variable term x here, I've got to do it to the constant 5 pi over 7 as well. So that's going to change him to a plus 5 pi over 7 in this instance, and that plus 6 is just going to hang out here for mostly just for the ride. We'll separate this guy off. And so now is when we're going to use this even property of cosine, since we've got the negative isolated inside the parentheses. So we have now 8 cosine of 4 pi x plus 5 pi over 7, and still with that plus 6 back here at the end. Alright, so this is now the function that we are going to be focused on graphing for the rest of the way. Oh, forgot the y's in front of these. Alright, now the first piece of information we're going to look at here is just to find the amplitude, which is going to be the absolute value of our coefficient of the cosine, which is 8, and its absolute value is 8, so we're good to go there. Next up, we're going to look for our period, which is 2 pi over whatever our coefficient of the x was inside the parentheses here, which was 4 pi. And the pi's are going to go away here. So we're going to be left with a positive 1/2 here for our period. All right, now, the fact that there's no pi present here does not mean there was a mistake or anything like that. It does happen from time to time. It doesn't happen a lot in many textbook examples, but it is a viable answer for a period. Next, we're going to look at our phase shift. We know there is one since there was something being added or subtracted inside the parentheses with the variable. And so here we're going to take our constant 5 pi over 7 and divide it by the coefficient of the x, which was 4 pi. Now this gives us a complex fraction, which is particularly irritating. So what we're going to do now is, instead of looking at this as a fraction being divided by something else, which can be kind of unwieldy, we're going to take and look at this as 5 pi over 7 times the reciprocal of that thing we're dividing by, 4 pi. So that's going to be times 1 over 4 pi. Now the pi's are going to go away just like they did for a period, and unfortunately we cannot do anything else here, so that's going to leave us with a period of 5 over 28, or excuse me, a phase shift of 5 over 28, and I screwed up. That would be a negative. Alright, that I feel I can recover from here. The next element we're going to look at is our phase shift. Now, since we have something that's being added inside of our parentheses here, namely this 5 pi over 7, that's going to tell us that we are going to have a phase shift here. So, okay, great. We're going to take that 5 pi over 7 and divide it by the coefficient in front of the x, which is 4 pi. Now, there's an additional piece of information that you have to take into account here, and that is that by default, things inside the parentheses are a subtraction. So what we're going to deal with here is this guy is typically a minus. in the kind of generic formulas for graphing of a cosine. The fact that it's a plus here isn't a big deal, but that just means that that 5 pi over 7 is negative instead. Right. Now, taking this negative 5 pi over 7 and dividing it by 4 pi is going to be irritating because this then gives us a complex fraction, which pretty much nobody likes to deal with. So what we're going to do instead is take this negative 5 pi over 7, and instead of worrying about dividing it by 4 pi, we're going to multiply by the reciprocal of 4 pi, which is 1 over 4 pi, because that's an equivalent operation here, and it's going to make this a lot easier to deal with. So the pi's are going to go away just like they did for the period, and we're going to be left with a negative 5 over 28. If it were possible, we would reduce down any further than the fraction, but unfortunately, that's all we've got. Next, what we're going to look for is our distance between key points. And we're going to take care of that by looking at our period, which was 1/2, and multiplying it by 1/4. It's always being multiplied by 1/4, whatever our period is here. And so 1/2 times 1/4 will give us 1/8 for our distance between key points. Now we would also look to see if we've got a reflection. And now there was a negative sign inside the parentheses, but remember we were able to simplify that out using the even property of cosine. And as a result, there is now no reflection. And then lastly, we'll take a look and see if we've got any kind of vertical shift. And sure enough, we do, because back here, a +6, and that stayed with us through our simplification. So that vertical shift is going to be a +6. All right, now I've just rewritten everything here for us, including the more fully simplified version of our equation here. The y equals 8 cosine of 4 pi x plus 5 pi over 7, and that whole thing +6. And then we've got our amplitude of 8, period was 1/2, phase shift was negative 5 over 28. Our distance between key points is 1/8. We have no reflections to deal with, and a vertical shift of 6. So what we're going to do now is get started on our graph, since that was in fact the whole point behind the problem here. So we'll just draw our x and our y axes. Typically, we would be taking this and going between positive and -8. But that doesn't take into account our vertical shift, which is, of course, going to be kind of an important deal here. So if you've gone ahead and drawn yours and you think you didn't leave yourself enough room, just go ahead and start over just like I did here. And so we're going to have our center line for this graph here at +6. So we'll put our x and our y axes a little bit friendlier here. So we'll call this our center line here of +6. And we'll just draw it as a dotted horizontal line here to kind of help us with the whole visualization. Now with our amplitude, we are going to go 8 units up and down from that center line. So 8 units up will put us at a +14, and 8 units down will put us down here at a -2. And so these are the maximum and minimum values we're going to be dealing with. And so any place cosine would have been 0 previously is just going to fall on that center line of +6. And just like with any other graphing of a trig function, the first thing we're going to do is start with our phase shift, which was at -5 over 28. Now I'm going to just still mark that off on the x-axis here, and we'll go from here. Alright, now that we've got our phase shift, which is our starting point, taken care of, we're going to find the subsequent key points by taking -5 over 28 and adding our distance between key points to it. That was 1/8. Now 28 and 8, those aren't the same number, clearly, So in order to add these two fractions together, we're going to have to find a common denominator. And the closest, smallest number we can find here for both of those is going to be, let's see, 56. All right, so that's going to be multiplying top and bottom of the first fraction by 2, and top and bottom of our second fraction by 7. So we're left with a negative 10 over 56 plus 7 over 56, which will give us negative 3 over 56 for our next point here. So that's going to be the next key point, so we'll go ahead and put him down here on our graph, negative 3 over 56. And then we're going to take that negative 3 over 56 and add another 1/8 or 7 over 56 to it, which will give us positive 4 over 56. So that's going to be right about here. Then we'll add another 7 over 56 to get us 11 over 56. 1, 2, 3, 4, and we need another point here for a complete period. So we add a 7 more to get 18 over 56. Now I realize that some of these fractions can be reduced into lowest terms, but we chose not to do that because it makes finding the subsequent key points in our complete period here to be much, much easier if we leave that in the unsimplified form. Once we've got all of the points we need for our complete period, if you want to go back through and do the simplification, that is perfectly acceptable. Now the fact that we have a cosine for our key function here tells us that we're going to either start at the top or bottom of our graph, depending on where we were going to begin with. Cosine typically starts at the top, so that would be right about here. At our point, negative 5 over 28, comma 14. And remember, there were no reflections, so that's where we're going to stay. Though our next point would be at our 0, which means it's going to be back at our center line here at 3 over, or excuse me, at negative 3 over 56, comma 6. And then we're going to be all the way down here at the bottom. In fact, here, let me write it out this way so we'll actually be able to see what's going on. At negative 2 for our y value at when x is 4 over 56. Then at 11 over 56, we're back up here at the center line, positive 6. And then at 18 over 56, here we are at the very top of our graph, positive 14. All right, now that's our key points are drawn. All that's left for us to do is connect the dots. We'll try to do this as smoothly of a curve as we can. All right. So mine looks a little lopsided. That's just really more or less due to the fact that I'm drawing this by hand. But this does have a vaguely sinusoidal shape to it, which is really the best you can hope for when you're doing all of these things by hand, as long as you don't have any sharp corners or kind of jagged marks down through here. You should be fine as far as your grading of your graph goes. And that's all we have. This is our complete period graph of y equals 8 cosine of 4 pi x plus 5 pi over 7 plus 6, which is our simplified form of the original equation.